We will hear about rare earth-free motors for medium and high power electric vehicles. We have two authors, Marco Villani from Italy and Fernando Nuño. Both present a project by the European Copper Institute. Fernando Nuño, also an old colleague, energy engineer, worked in the development of combined heat and power plants, joined the French Energy Regulatory Commission, worked in the automotive sector at Renault, and he's with the Copper Association since 2007. Thank you very much. You have the floor.
Ladies and gentlemen, good afternoon. It's my pleasure to be here with you today. First off, I would like to thank the Motor Summit organization for this opportunity. Today, I will talk about the ReFreeDrive project on behalf of all project partners, and more particularly on behalf of the co-author of this presentation, Marco Villani from the University of Aquila. The ReFreeDrive project develops electric drives without rare earths. It started late 2017 and will last till March 2021. The project has been funded by the European Union's Horizon 2020 Research and Innovation Programme with a budget of €6 million. Taking the Tesla S60 motor as a benchmark, the project has increased specific torque by 30%, reduced motor energy losses by 50%, achieved a 15% cost reduction, and increased power density in power electronics by 50%. Why rare earth free? Well, because of multiple reasons. The most important one is the high degree of criticality both in terms of supply risk and reliance for the clean energy. Second, the cost, which is higher than that of other technologies. Additionally, the price can be highly variable. The graph on the top right corner shows the dysprosium and neodymium price spikes that took place a few years ago. Last but not least, the environmental balance for permanent magnet is significantly worse than that of base metals such as steel or copper. Now the point is whether we are replacing rare earths with other elements that can be subject to availability problems. The answer is no, as far as copper is concerned. There are sufficient mining and recycling copper reserves and resources worldwide to cope with renewables and e-mobility growth. The primary route is mining, which represents about 70% of the copper supply. With an annual production of about 21 million tons, there are reserves for at least 40 years. But that's not all. Identified resources go up to 100 years availability. Total resources are estimated to reach about 250 years availability. And this doesn't include deep sea deposits, the multimetallic nodules, which are rich in metals, including copper. Together with this, the secondary route, which is recycling, provides about 30% of the demand for copper. It's important to remind that copper can be recycled repeatedly without downgrading, and also the fact that most copper alloying elements can be recovered as well. The ReFreeDrive project has developed 8 motor variants, 2 power levels, 75 and 200 kilowatt, induction machines following 2 different manufacturing routes, fabricated copper rotor and die-cast copper rotor, ferrite-assisted synchronous reluctance machines, and pure synchronous reluctance machines. Here we show the main KPIs, the benchmark values, and the project achievements. The table on the top shows the results for the 200 kilowatt version, which is compared against the Tesla S60. As you can see, the objectives have been achieved for the 3 technologies, both in terms of specific peak power density, specific peak torque, maximum speed, and peak efficiency. The bottom table compares the 75 kilowatt version with the Nissan Leaf, which is a permanent magnet motor. Here, ReFreeDrive models achieve good peak efficiency and rotational speeds, but fall shorter in peak torque and power density. The ferrite-assisted synchronous reluctance motor, however, achieves high specific peak power, even above the benchmark motor. It's important to indicate here that the designs have been optimized for the 200 kilowatt version. Then the 75 version shares the stator and rotor designs and dimensions with shorter lengths and uses lower voltage levels and lower rotational speeds. The audience should therefore look at the 200 kilowatt version to understand what the technology can really deliver. A comparison exercise between the three technologies has been carried out by Jaguar Land Rover, one of the project partners. DC voltage is 720 volts. Maximum current depends on the technology. It ranges between 500 and 636 ohms. The apparent power required at the inverter level is 430 kVA for induction and 550 for synchronous reluctance. Peak torque is 380 Nm for induction, 415 for pure synchronous reluctance, and 470 Nm for Ferrite-assisted synchronous reluctance. In terms of peak power, the induction motor achieves the highest values, 300 kilowatt, with 150 kilowatt at maximum rotational speed, while synchronous reluctance models remain below these figures. The rotational speed is 18,000 RPMs for synchronous reluctance and 20,000 RPMs for induction motor. This introduces a slight bias in terms of comparison between the technologies because mechanical losses increase at higher rotational speed. A system-level analysis is carried out. This takes into consideration the efficiency maps of the motor, the inverter, and the gearbox. The EPA cycle points are represented in these maps, and the weighted average efficiency of the system with the three components is determined. The results are shown here. The Ferrite-assisted synchronous reluctance motor provides the best overall efficiency with quite limited losses in the motor thanks to a reduced current demand for the same operating point. The pure synchronous reluctance motor and the induction motor perform quite similarly. The pure synchronous reluctance motor has higher inverter losses, while the induction motor is penalized by the higher rotational speed, which creates higher losses in the gearbox. The results presented so far are for the EPA efficiency cycle corresponding to the first line of the table here. However, if we carry out the same exercise for other drive cycles, focusing on different performance characteristics, we'll find that pure synchronous reluctance outstands in the high fuel economy test cycle, while induction has the best performances at highway cruising speeds and beyond. So there is no winner or loser. Each technology can be ideal depending on the purpose. What are the next steps in the project? The manufacturing of prototypes has just been carried out, and now we are proceeding with the integrated powertrain testing. The 75 kilowatt version will be integrated in a Mercedes Vito and will follow in-vehicle tests early next year. Now we show some pictures of the prototypes. This is the pure synchronous reluctance rotor and stator. As mentioned before, the 75 kilowatt version is a derivative of the 200 kilowatt version, showing its design and dimensions, apart from the length. Here we can see the motor with its housing, the power electronics module, and its housing as well. In this picture, we see how the two housings match together. It's important to mention here that the cooling system is shared between motor and power electronics. Here we focus on the induction motor prototype. In the upper left pictures, we can see the stator with a particular detail on the hairpin winding. On the top right, we can see a detail of the inverter box and the motor assembly. Then, on the bottom, we have some pictures of the die-cast version on the left, then the fabricated rotor cage on the right. A few more pictures of the stator, the rotor, and the final assembly in the external housing. And now some pictures of the pure synchronous reluctance motor. On the left, we can see the laser cutting operation of the electrical steel laminations, and on the right, the final stack. A couple of pictures of the ferrite-assisted permanent magnet motor. And as mentioned before, the 75 kilowatt version will be tested in a vehicle for which a series of integration elements are needed, such as the cooling system, the gearbox, the battery pack, the charger and converter, and certain control units. So here we come to the end of this presentation. I would like to go through ReFreeDrive partners. First, University of Aquila, in charge of pure synchronous reluctance designs and manufacturing, co-author of this presentation. Motor Design Limited, in charge of the induction motor designs. Jaguar Land Rover, which has specified the requirements for the 200 kilowatt version and carries out the techno-economic analysis of the 4 motor versions. Marvel, which integrates the prototypes in the vehicle and checks potential exploitation routes. R13, in charge of the power electronics design and production. IFP Energy Nouvelle, in charge of ferrite-assisted synchronous reluctance machines and motor testing. Aurubis, in charge of the fabricated copper rotor cage for the induction machine. Bergman, in charge of the die-cast copper rotor cage. Fundación Ciudad for the project management and coordination. Technomatic, the provider of the hairpin winding technology. Centro Sviluppo Materiali, in charge of the analysis of multiple electrical steels. Privé, in charge of establishing the boundary conditions. And the European Copper Institute, which promoted the concept, the funding, application, and is in charge, together with the University of Aquila, of communication and dissemination activities. For more information, please be in touch with us through our website, LinkedIn, or directly by email. Many thanks for your attention.
Thank you very much, Fernando. Now, if everything works. Oh, hello. Buenas tardes, Fernando. Buonasera, Marco. Thank you. Can you hear me?
We can hear you, yes.
But I don't hear Marco. No, I can see your beautiful face. I can see move your lips, but I don't hear anything.
Now?
Now is much better. Okay. Welcome you too. Congratulations for an excellent presentation, Fernando, and congratulations for both of you for an excellent background research on the topic of beyond rare earth, I think, beyond rare earth. Rare earth has helped us to get into some technology, and now with the scarcity of the material, we are already starting to look beyond that. I think it was very interesting because you also have already some prototypes, or maybe more than prototypes working. That means last time we talked about that 2 or 4 years ago, it was more a theoretical approach, but now we are getting much more clear. Actually, I didn't introduce Marco. Marco is a professor of electrical engineering in L'Aquila. L'Aquila is a beautiful Italian town, about 120 kilometers from Rome. Therefore, a very interesting university with Marco and some other colleagues who have done very foremost research in the field of electric motor technology and advanced technology. Now, let's talk a little bit about these rare earth-free motors. And if I understand correctly, a synchronous reluctance motor, rare earth-free,
yes,
is the solution for your problem.
Yes, the synchronous reluctance motor doesn't have winding and permanent magnet in the rotor. We are working on this field from several years, and this motor could represent a valid alternative to the rare earth solutions because it is very simple to manufacture. It presents a robust rotor structure we have designed this motor within the ReFreeDrive project, and we have also realized the prototype and tested this motor with satisfactory results. Fernando has presented the comparison among the induction motor solution and permanent magnet assisted solution, and our design presents good performance, and in our opinion could be a very interesting and valid alternative for the electrical vehicles.
Okay, and the solution to be magnet-free in a permanent magnet motor is to use ferrite.
For the permanent magnet assistance, yes. Our partners have used the low-cost permanent magnet ferrite. The insertion of the ferrite inside the rotor allows you to improve the torque and also the power factor of this motor. But the solution, permanent magnet assistance, it is a low-cost solution because the cost of ferrite is very, very low respect to the neodymium iron ore.
Very good. Low cost is always an advantage. But another question, can you start your synchronous reluctance rare earth-free ferrite motor without a variable frequency drive?
No, in this application, the motors are fed by drive, because in electrical vehicle we have to change the speed of a motor, and in this application the drive is necessary. We have realized for industrial application light start synchronous reluctance motor for industrial application, because if you insert the squirrel cage in a rotor of synchronous reluctance motor, you have a line start high efficiency synchronous reluctance motor fed by the grid without drive. But for the electrical vehicle, the drive is necessary.
Okay, I understood from the presentation from Fernando, the project you are reporting is mainly for automobile engines, motors, okay? And
yes.
Now Marco was mentioning, and I was hinting at that, the technology, if it is good, the motor is efficient, it is rare earth-free, could also be used for stationary applications in factories. And there you might need a little bit speed variation, or you might not need a speed variation. If you don't need a speed variation, can you use a synchronous reluctance motor without having a variable frequency drive?
For the no drive application, we can use synchronous reluctance motor with the squirrel cage, but for the industrial sector, not for automotive.
Yes, I talk about industrial.
For the industrial,
you confirm
yes,
that you can operate, start, and run a synchronous reluctance motor for stationary application. Because I'm asking, what is the development from the automobile side, giving as a profit for the stationary industry side? Can this development you're researching and you're making prototypes and you're having first successful applications also benefit industrial applications?
Yes, of course, yes. These in our research, we have demonstrated that the synchronous reluctance machine without permanent magnet, low cost, or with the low-cost ferrite represent an interesting alternative for the induction motor and rare earth motor, not only for automotives, but also for the industrial application. In the industrial application, we have seen the previous presentation. ABB has presented the synchronous reluctance motor with very high efficiency, but it is not very popular up to now because only a few percentage of this motor are applied in the industrial field. We think that line start synchronous reluctance motor in the future can guarantee very high efficiency at low cost.
Now
our university are working on this field.
Thank you, Marco. I'd like to ask a question to Fernando.
Please.
Fernando, when we talk about rare earth, Copper Institute is in favor. When we talk about synchronous reluctance, do they still use copper?
Yes, well, the stator still uses copper. In the project, we have developed two rare earth-free technologies. So we have focused the Q&A so far on the synchronous reluctance, but the induction motor with a copper rotor is the other technology route, which doesn't use any rare earth, and which provides also good response to the requirements of the e-mobility project in this case.
And that
also
is using a copper rotor.
That is using the copper rotor, and the copper usage is higher than in the synchronous reluctance
Okay,
option.
but it's interesting that you compare the different technologies, the normal induction motor, the copper rotor induction motor, and the permanent magnet rare earth-free motor. And obviously, if I understand it well, the big advantage of a synchronous reluctance technology is that you can make a variation of speed very easily. Therefore, it lends itself to automobile use, right?
Yeah. Well, it's also the case for the induction. In both cases, for automobile applications, as mentioned by Marco, are driven by VSD. Because we need speed variation for automotive. So both solutions fit with the requirements, and both could be translated back to the industrial sector. Of course, with some adaptations and probably using less technological advances. For instance, hairpin winding might not be such a requirement, but might be welcome as well for some applications in the industrial applications.
Okay, guys. Thank you, Fernando. Thank you, Marco. It was an interesting presentation, interesting to talk to you. I wish you all the best, stay healthy, and we see you next time, hopefully live in person. Bye-bye, Fernando. Bye-bye, Marco.
Right. Bye-bye.